So with n variables, the order one condition remains the same, of course, because again, if we've got an optimum value, it has to be an optimum for all partial functions. So we need that the gradient, all the partial derivatives are cancelling, so we need that the gradient is equal to 0. Now we need some criteria for the order two condition to tell us what is going to be the sign of the second order term in the Taylor expansion. Okay, the sign of this term, because again, I've got that at the optimum value, my gradient is equal to 0, so that terms is cancelling. So the sign of the difference between f of x star and surrounding value is going to be given by this second order term. So I forgot the 1/2, but there's a 1/2 here. Okay, so that's about the same thing. Anyway, in terms of sign, they are going to have the same sign. So we need to study the sign of this term. This has a specific name, which is called the quadratic form. Okay, and so what we want to know is whether this is always positive, negative, or again, does it depend on the direction of the increase k that we are doing around that critical point. Okay, so we need to study that point. What can we know? So again, there was a 1/2 that should happen here, but for the sign, it doesn't change anything. What do we know about this H matrix? Okay, what can we do? What do we want to do? Where are we going to? Okay, so first a definition, because we're going to use that term. Positive definite, maybe it reminds you of something we dealt with when we were studying the inner product. So that's good, because this is related to inner product. So positive definite just simply says that a matrix is going to be called positive definite if ever the expression, so exactly the same expression we want to do, meaning you've got your matrix, it acts on items x that belong to some Rn space. So m times x makes something in if x belongs to Rn. If your matrix then belongs to n times n matrix, the product m times x itself belongs to Rn. And I'm taking, so m times x, belongs to Rm, and I'm taking the inner product, the dot product of this thing with x also. Okay, so that's something that is in Rn, something that is in Rn, we're taking the dot product of the two. All right, so that's making something in R. The dot product, in general, the inner product, that's the same stuff. Okay, all right, so we're going to say that a matrix is called positive definite if ever this thing is always positive. Okay, and positive definite if this thing is always negative. Right, that's just a definition. Now, what we would like is, if we want to make this greater than 0, smaller than 0, or it depends, we want to know whether our matrix is positive definite or negative definite, or not any of these. Right? So that's what are going to be the second order conditions. Once we've got a critical point, so one where the gradient is equal to 0, okay, we've got a critical point. We form the Hessian matrix of that. If your matrix is positive definite, then we've got a local minimum. And if your matrix is negative definite, we've got a local maximum for your function. Okay, so this is really what we want to determine for our matrix. For that, hopefully we remember something. We remember that our Hessian matrix is not any kind of n times n matrix. It's a symmetric matrix. And we learned something absolutely essential for symmetric matrix last year. So that's the spectral theorem, any real symmetric matrix is diagonalizable in an orthonormal basis, and its eigenvalues are all real. Okay, so what does it mean? The fact that is diagonalizable in an orthonormal basis is that I can write this. Okay, I can find a basis of eigenvectors that go in my matrix Q. such that I can write my matrix M as Q, D, Q transpose, and the diagonal matrix D only has real values. Okay, so that's a very powerful theorem. All symmetric matrices are diagonalizable in R. That's great. And so how can we use that? So let's rewrite what we're looking for, again with the 1/2 that would be better. Okay, so this is, we rewrite the fact that we've got symmetric Hessian matrix as this thing, and we expand it. Okay, so this is the product we're looking at. I'm just rewriting it here with one notation for dot product. If you've got X dot product Y, you can consider it as Y transpose times X in terms of row matrix times orthogonal matrix, so that you get a real value. Okay, so we rewrite it this way. We expand the matrix H as QD Q transpose, and then we can really rewrite that it's something Q transpose K transpose, so that's this part here. You've got your D matrix, and then you've got that second part here, Q transpose K here. All right, so that you've got really something looking like Y, D, Y transpose, D, Y. And if you expand that, what you're going to have as D times Y is just going to be, if you've got a vector Y1, Y2, etc., Yn, if you multiply it by lambda 1, a diagonal matrix lambda, so that stuff is making the vector lambda 1, Y1, lambda 2, Y2, etc., lambda n, Yn. And we take the dot product with Y, Y1, Yn, okay, dot products, that's making lambda 1, Y1 square plus lambda 2, Y2 square plus etc., lambda n, Yn square. Okay, so this is it. Oh, it's not an H, it's okay. So this is, in the end, the whole stuff that we have can be written as the sum of eigenvalues of your matrix times some squares. So that it's very simple to say when it's positive or negative, because we're multiplying some eigenvalues by some positive stuff. So if in the end, if all of the eigenvalues are positive, you just sum positive stuff. If all of your eigenvalues are negative, you're summing some negative item terms. And if some of the eigenvalues are positive and negative, it depends whether you had a very large amount for the corresponding I component here. Okay, so we can directly express it like this. Our second order condition now becomes, if all the eigenvalues are strictly positive, then we've got a local minimum. If all the eigenvalues are strictly negative, we get a local max. If they have different signs, we get a saddle point. And if some of them are equal to 0, then again, we are in those limit cases where we cannot conclude about it. Okay? If you don't want to calculate the eigenvalues, you've got this criteria, which I believe is slightly more complicated than just calculating some eigenvalues, one for good, which is saying that instead of looking at the eigenvalues, you look at the determinant of some submatrices, some square submatrices that you can create. And if all the minors are positive, you get a positive definite matrix. If they are alternating beginning with -1, you get a positive definite negative matrix. Okay, so you can use either of the two criteria for this. Okay, so you know everything we need to know for optimization of functions of n variables when we have functions that are two times differentiable.